After introducing the kinetic energy of a body or a system, we can determine the relationship between its change and the work done on the body or the system. This relationship is formulated in the work-energy theorem presented here. We have just determined the work W done by a constant force F acting on a point mass m when it is accelerated from rest to a given speed v, and we found that it is equal to 1 over 2 times the mass m times the square of the speed v. This work is done while the point-like body is accelerated over a given distance, and the formula can also be applied to compute the works done when the moving point mass covers the distances s1 and s2. The work W done on the point mass by the force F when it moves through the distance s1 minus s2 is equal to the magnitude of the force F times the distance s1 minus s2, or F times s2 minus F times s1, which is the difference between the works done on the point mass covering the distances s2 and s1 respectively. If we substitute the formula derived for the work into the two terms, we obtain 1 over 2 times the mass m times the square of the velocity v2, minus 1 over 2 times the mass m times the square of the velocity v1. In the result we can identify the quantities measuring the kinetic energy of the point mass when it is accelerated from rest to the speeds v2 and v1 respectively. Now we can formulate the work-energy theorem as follows. The change in the kinetic energy of a point mass m is equal to the work W done by the force F acting on the point mass, that is 1 over 2 times the mass m times the square of the velocity v2, minus 1 over 2 times the mass m times the square of the velocity v1 is equal to the work W. Here the velocities v1 and v2 are the initial and the final velocities of the point mass accelerated by the force F performing the work W. This theorem holds for the general case as well, where the force F is not constant and the point mass m travels along an arbitrary curve C between the points A and B. We can prove the theorem for the general case by calculating the work done when the point mass is only a small displacement along the curve. The infinitesimal work done on the point mass by the force F through the infinitesimal displacement ds along the curve is equal to the scalar product of the force F and the displacement vector ds. Since the instantaneous velocity v of the point mass moving along the curve is defined by the derivative of the displacement s with respect to the time t, the infinitesimal displacement vector ds and its scalar product with the force F can be written as the velocity v times the infinitesimal time interval dt. If we apply the second law of motion expressed in terms of momentum, we can write the force F exerted on the point mass as the derivative of the momentum p of the point mass with respect to the time t. Here the time derivative of the momentum p times the differential dt of the time is equal to the differential dp of the momentum. Because the momentum p of the point mass is defined by its mass m times its velocity v, the scalar product of the force and the displacement vector is given by the mass m times the scalar product of the velocity v and its differential. This result can be substituted into the work W done by the force F along the curve C between the points A and B, which is equal to the line integral of the force F with respect to the arc length s along the curve C between the points A and B. Then we can transform the line integral into the mass m times the integral of the force F with respect to the velocity v along the curve between the velocities v1 and v2 of the point mass measured at the points A and B. If we perform the integration, then we obtain m times the square of the velocity v over 2 evaluated at the lower and upper limits of the integral, which gives 1 over 2 times the mass m times the square of the velocity v2, minus 1 over 2 times the mass m times the square of the velocity v1. This proves the theorem. The work-energy theorem will help us to derive one of the most important law in mechanics, the law of conservation of mechanical energy. In order to do so, we will apply the theorem for the most general motion of a point mass under the influence of gravity, which is projectile motion. When we studied projectile motion, we proved that the trajectory of the projectile is a parabola. The motion of the point-like projectile along this parabola can be described in a Cartesian coordinate system attached to a frame of reference, where the z-coordinate measures the altitude of the moving projectile. Let us consider two arbitrary points A and B on the parabola with the vertical coordinates z1 and z2, where the instantaneous velocities of the point mass are denoted by v1 and v2. We already determined the work W done by the gravitational force when a body of mass m moves from one point to another one, for example from the point A to the point B. Then the work W is given by minus the mass m times the magnitude of the gravitational acceleration g times the vertical distance of the points A and B, that is z2 minus z1. If we substitute this result into the work-energy theorem, we can write that 1 over 2 times m times v2 squared minus 1 over 2 times m times v1 squared is equal to minus m times g times the difference between z2 and z1. Then we obtain the equation stating that 1 over 2 times the mass m times the square of the velocity v1 plus the mass m times the magnitude of the gravitational acceleration g times the height z1, is equal to 1 over 2 times the mass m times the square of the velocity v2, plus the mass m times the magnitude of the gravitational acceleration g times the height z2. The first terms in both sides of the equation measure the kinetic energy of the projectile at the points A and B respectively. Similarly, the second terms in both sides of the equation measure the potential energy of the projectile at the points A and B. As a result, we can write that the sum of the kinetic energy and the potential energy of the point mass at the point A is equal to the sum of the kinetic energy and the potential energy of the point mass at the point B. Generally speaking, the sum of the kinetic energy and the potential energy of the point mass is the same at every point along its path, that is, the sum remains constant during the motion of the point mass in the gravitational field. As the projectile increases, the decrease in its kinetic energy is equal to the increase in its potential energy. As the projectile falls, the increase in its kinetic energy is equal to the decrease in its potential energy. In other words, the kinetic energy and the potential energy transform into each other in the motion under the influence of gravity. This statement not only holds for gravitational force but also for conservative forces. We call a force conservative force if it does not change in time and the work done by the force along an arbitrary path connecting two points depends only on the positions of the points, but does not depend on the path itself. This definition also shows that the gravity is a conservative force. Now we can formulate the law of conservation of mechanical energy as follows. If the net force F acting on a point mass is a conservative force, then the sum of the kinetic energy and the potential energy, that is the total mechanical energy E of the point mass, is constant.